So we missed the previous Monday class. Sorry for the inconvenience and then rescheduling of this class. So I will post the recorded class. Actually, so today's class is for day 3, right? So it's a day 3 class, and then I will record the day 4 class, and then I will post the recorded class until the next September 24, before September 24. Okay, so I will review what you learned in the previous class. So we learned about the performance metric of computer systems in the previous class. So we started from the fact that so there are various types of performance metrics, and then we need to use some appropriate performance metric for the purpose of a system. So we took the analogy of an airplane, and then actually for the airplane, we learned that so various types of performance metrics can be used. And then actually there are two types of performance metric in the computer systems, so response time and throughput. And then actually this is very important. So you need to remember the definition of you need to remember the definition of response time. So I mentioned that this is latency, and then the definition of throughput. Definition of throughput. So for this throughput, we use the metrics like megabyte per second or flops, like floating point operations per second. So actually the performance metric of response time and throughput look similar each other, but we need to distinguish it, okay? Response time and throughput. Also, in this course, we define the performance of a computer system. So this is a definition. So that means you need to remember the definition of performance of a computer system. So what is the definition? So performance is 1/, execution time. So in order to measure the performance of two different computer systems, we first need to measure the execution time. Okay, so this is the definition. So you need to memorize the definition. Okay, and then if we say so computer system X is n times faster than Y, so that means we need to we are comparing the performance of two computer systems. So we can use the equation like this performance X divided by performance Y, and then by the definition we can use the execution time. So when we compare the performance of a computer system X and Y, then we just compare the execution time of Y with the execution time of X. So execution time of Y divided by execution time of X. So you need to remember that, so this is the performance. So the performance is inversely proportional to the execution time. So when you are asked about the performance of the system, then you need to measure the execution time, okay? And then we learned that we will focus on CPU time, not the entire elapsed time, because I said the computer system is very complex. So if we just measure the entire software execution time under our normal computer system, then it will include the various types of overhead and I/O time, and then some other impacts. So in order to measure the performance of a processor or CPU fairly, so we just focus on the CPU time. So CPU time means that we just exclude every overhead, like operating system overhead or input and output device overhead. We just measure the execution time in CPU, it's a processor. It is because in the computer system, the CPUs execute instructions. And then I also explained that our software, this is software, the software, software, the software is translating the instruction, and then these translated instructions are executed by CPUs. That's why we focus on the CPU time. The CPU time is just the execution time. That means the response time. Okay, so this is the equation of the CPU time. So it's the CPU clock cycles to execute a certain application, and then clock cycle time. Okay, so we can. So in order to measure the CPU time of one application, we just count the CPU cycles to execute a certain application, and then these cycles, number of cycles are multiplied by clock cycle time. That means the clock period. And then we can rewrite this equation like instruction count multiplied by CPI and then clock cycle time. Okay. So actually, we frequently use this equation, not this equation. So CPU time is, so you need to remember this equation. So this is very important equation. So instruction count multiplied by CPI and then clock cycle time, okay? And then we learned how to measure the CPI, because CPI is it's a very important concept. It's a very important performance metric in the processor. Okay, I will explain later. And then also you need to remember that the CPI varies by the combinations of various type of instructions. Okay, also by different instructions, different instructions may have different clock cycles. Okay, so you need to remember that. So this CPI is determined by architecture of processor. So we usually, I said usually, not always, okay? We usually assume that for every processor takes one cycle per instruction. That is our assumption, but not real. That is not real. So actually in reality, the processor takes different cycles for different instructions. So that's why CPIs can be different for the different applications. Why? So this is the application A, oops. This is A and the application B. And then actually different applications have different fractions of instruction types, okay? For example, this application A has the 5 adds and 1 multiplication. And then application B has 5 multiplication and 1 add instruction. And then I said the multiplication is more complex than add instruction. So that means the multiplication instruction, not always, but it will take more cycles than add instruction. So because these fraction of instructions are different for the different applications, the CPI can be also different for the different application. Okay, so you need to remember this. Okay, so we learned how to measure the CPI for the different applications. And so that means if the these fractions of instructions are provided, then we can calculate the CPIs for each instruction. Okay. So do you have any questions for what we learned in the previous class? Okay, good. So I will move on to today's topic. Okay, this is the summary. So finally, we have equation of the CPU time. So this is CPU time is the instructions, the number of instructions per program. So that is the instruction count. So we frequently use the IC because it's instruction count, and multiplied by number of clock cycles per instruction, right? So this is the CPI, and then multiply by seconds per clock cycle. That is the clock period, clock cycle time. So this is the clock period. We frequently use the TC for the clock period. So IC multiplied by CPI multiplied by CPI multiplied by TC is the equation of the CPU time. That is the, we frequently use the execution time. So this is the equation of the CPU time we frequently use in the computer or normal computer system. And then I already mentioned that if we see this equation, then we can explain the factors that influence the performance of a computer system. So we need to explain, okay? So how can we, so in order to increase the performance of a computer system, so firstly, we need to reduce the execution time. Then in order to reduce this execution time, how can you reduce this execution time? It's very simple, actually. So we can reduce one of these factors, the instruction count, or CPI, the clock per instruction, or we can also reduce the clock period, okay? So how can you reduce these factors? So there are some different factors like to influence the performance of a computer system. So first, we can consider the algorithm, the algorithm of an application. So algorithm decides the instruction count. Actually, so if we use the different algorithm, that means that we write the different application. So also, so there are different kind of algorithms, such as the normal sort or quick sort. So we can expect that the quick sort is faster than normal sort because its name has quick. Huh? Okay. So, but this is the same sorting application, but we apply the different algorithm like normal sort or quick sort. And then this quick sort will be faster than normal sort. Why? If the quick sort is compiled, then quick sort will generate less instruction count. Okay, so algorithm affects instruction count. So in order to reduce the in order to increase the performance of a computer system, then we need to use the better algorithm. Okay, that's why we learn the algorithm in the computer engineering department. So algorithm is also very important. And then programming language. So I also explained that the C is, if we use C, instead of Python, then the speed of the application will be much faster. Okay, so this programming language also affects the instruction count, also CPI. So different application is generated, so the CPI can be different. And compiler. So compiler is the translator that translates our high-level language into machine language. So, and then also there are many different techniques of a compiler. So if we use the better techniques or better optimization techniques for the compiler, then the speed of the application will be faster. So if you know about the GCC compiler, it's a GCC. So GCC means the GNU C compiler. Okay, so this is the compiler for C language because it's a C compiler. And then we can use the different option for this GCC compiler. So for example, if we can use the -G option, also we can use the -O1 or -O2, -O3. So G means the no optimization is applied. So this is not optimized version. And then this O means the optimization level. So O3 is the most optimized techniques will be applied. So if we use the better optimization techniques for the compiler, then our compiled application will be faster. It is because compiler also influences the instruction count and CPI. Okay, and then instruction set architecture like x86 or ARM or RISC-V. So these are the different types of instruction set architecture. Okay, this instruction set architecture affects the all factors like instruction count, CPI, and also clock period. Okay, so this is very important. This is the equation, and then if we see this equation, then we can know which factor will affect some result of the equation. That's it. And then if we can distinguish the different factors, and then we can focus on some factors to increase the performance of computer system. Okay, that's why equation is important. Okay, and then let's learn about some different type of performance metric called MIPS. Okay, so MIPS means the millions of instructions per second. So this is MIPS. So this is called MIPS. Okay. And then if we see the name of the MIPS, actually definition of the MIPS, then we can know what MIPS means. Okay. It's actually the number of instructions executed per second. That is the definition of MIPS. So I already mentioned that if the software A is translated, then instructions are generated by compiler. And then if the more instructions are executed by processor, then we can say that, oh, this processor is faster than other processor. And is that right? Right or not? So So you need to know that. So you need to remember that if we want to compare the performance of two different systems, just first we need to measure the execution time. So, but MIPS just mentioned the number of executed instructions per second. Okay, so it's slightly different. It is not exactly execution time, not exact execution time, right? If the same number of instructions, so I said the same number of instructions are executed by different processor, so A is compiled and then the instructions are generated, and this application will have the same number of instructions. And then these compiled applications are executed by processor A, or is a processor B. And then processor A has the higher MIPS number, higher. And so MIPS is lower. So which one is better processor? Which one is better? This one is better, right? Because instruction count is the same, and then more instructions can be executed per second. That means processor A will have shorter execution time, right? So PA will be better. But this is true only when the same number of instructions are executed. So I said the same number of instructions are executed. Okay, what does that mean? This is the application A, and then application A is compiled by -G option. Okay, so and then also the same application A can be compiled by -O3 option. And then I mentioned that O3 option means that this the more stronger optimization techniques will be applied. So instructions are generated from the same application, but the different compile options are applied. So this instruction count will be larger. For if we use the -G option, it's a no optimization option. And then if we use the more optimized option, then instruction count will be smaller. And then these different instructions are executed by the same processor, which has the same MIPS number, but this will be more high. This will have the higher performance because we use the -O3 option. It's the more optimized option. So what does that mean? Even though the MIPS is the same, it's the same processor, the MIPS number is the same, but based on the instruction count is after the compilation, then the performance can be different. Or this is a little, I believe, this is a little bit confusing because for the same number of instructions, we can use the MIPS as the performance metric. But for the different situation, like a different number of instruction count, we cannot directly use MIPS as the performance metric. Okay, so you need to remember this because this is a little bit confusing. So actually, we frequently use the performance rate metric like FLOPS. It's the number of floating operation per second. So and then actually this FLOPS metric is very important for measuring the performance of high performance processor, such as GPUs or high performance CPUs, because recently the machine learning applications or some other parallel processing application or scientific applications are very important. Okay, for example, the neural network applications frequently use this floating point data type. Okay, that's why the flops are important. But flops are very similar to these MIPS because that means the number of floating point operations per second. So that just measure the number of executed floating point operation per second by processor. So if this is the same application, and then by the different compiler, this operation may generate the larger floating point of instructions, or this compiler may generate the less floating point instructions. So in this case, we cannot measure the performance with these flops. Okay, so just remember that. So we learned about the definition of performance. So just remember that in order to compare the performance, we need to measure the execution time. So, okay, because this is definition. We can use some different type of performance metric, such as MIPS, the number of instructions per second. But in order to use the MIPS for the performance metric, then some conditions should be met. So this for this condition is the instruction count, the same number of instructions. So same instruction count. If the same instruction counts are generated from the application, we can use MIPS as the performance metric. And if not, we cannot use MIPS as the performance metric. Okay. So this is a little bit confusing. So that means, so I will make I make a question for this MIPS in midterm exam. Okay. Okay. So we learned about the performance of a computer system. So now, we will learn about the power consumption. That is the cost of a computer system. So computer system is an electric device. That means we need electric power to run a computer system. So computer system actually consume electric power, and then that is the critical cost to run the computer system. Okay. So for example, so we use air conditioner during summer because summer is very hot. But if we turn on the air conditioner, so we frequently think about the cost of the electric power, like so the cost of the air conditioner. That means the running cost of a system. And then the computer system is the same. If we need electric power to run the computer system, so we need also focus on this running cost of the computer system. Actually, this is very critical factor of the computer system. So usually we are engineering students, so we focus on the performance and cost. Actually, that is our goal of research. So we need to increase the performance while we need to reduce the cost of the system. Then the power consumption is the some critical cost of the computer system. So let's learn about the power consumption of the processor. So this graph shows the change of the clock rate. That means the clock frequency of the CPU, and then power consumption by CPU. The metric of the power is the watt. So that means the energy per time, the consumed energy per time, right? So in 1982, the 8286 processor was launched, and then at the time the clock frequency was about the 10 megahertz. So 10 megahertz. And then power consumption is just the 3.3 watt. So usually our the application, it is called the application processor. That means the CPUs in our smartphone consume about the 5 watt. So less than 5 watt. But in 1982, desktop CPU consumes 3.3 watt. It's very low. Oh, it's very good. But how about the performance? Performance is also extremely low. The clock frequency is about the 10 megahertz. And then recently, not recently, because it's the 2012. So Core i5, the clock frequency of Core i5 is about the 3.4 gigahertz. Okay. But the power, how about the power consumption? The power consumption is about the 77 watts. So recently, the Intel CPU, they set some TDP. It's a typical power consumption level of the CPU. So Intel usually set the TDP as the 65 watt, and then clock frequency is about 3 to 5 gigahertz. So what is observed? So what can we observe? The performance of processor increases by time, and then that's obvious. That means the clock frequency increases, and power consumption also increases. So performance is increased. Also, the cost is increased. But around 2000, the clock frequency it's similar, does not increase. So in the 2004 Pentium 4 has the 3.6 gigahertz clock. Okay, but this clock frequency is nearly the same. And then at this time, the power consumption becomes about 100 watts. Oh, it's very high. But at the time, after this year, the power consumption is reduced. So actually, the power consumption is the restriction of our CPU manufacturing. If we increase this clock frequency continuously, then we can make the better CPU more easily. Okay, so we can just increase the clock frequency. But problem is that if we increase this clock frequency, the power consumption is exponentially increased. So that means if we want to use the better computer or better CPU, then our computer system will consume the power of some nuclear reactor. Okay. So if this trend is continuously maintained, then power consumption of the computer system may be similar to the power consumption of the nuclear reactor. Okay. So that's why the power consumption is the some limitation of the computer system manufacturing. And then this power consumption of the computer processor is usually determined by CMOS technology. That means the semiconductor technology. So this is the equation of the power consumption of typical digital systems. That means the typical digital chips. The power consumption of a digital chip is actually there is some vector like alpha, that is the activity vector, but in this equation, this activity vector is not shown, but so we can say that this is just proportional. Okay, the power consumption of the CMOS circuit is proportional to the capacitive load. That is the capacitor of a circuit, and then the square of voltage, supply voltage, and clock frequency. That is the equation of power consumption on CMOS circuit, so digital circuits. Okay. Actually, this equation is derivative. This equation is calculated from the some basic CMOS transistor technology. Okay, so but in this course we cannot learn about the detailed technology on CMOS transistor. So we can I will just explain what does these vectors mean. Okay, so I said the capacitive load means the capacitor of the CMOS transistor circuit. And then actually this capacitor is proportional to the area of a chip. So in the previous class, I showed the photo of CPU die. So you can see some very large number of transistors, and then if we just fabricate this large number of transistors, then it also occupies some areas. So this capacitive load is proportional to the area of chip. Okay, and then this voltage means just a supply voltage, and then frequency is the clock frequency. Okay, so if we use the larger chip, this capacitive load increases. And how about the voltage? So actually, in the previous time, we used the 5 volt for the supply voltage of the CPU, but recently we used the 1 volt for the supply voltage of CPU. So this voltage is reduced. How about the frequency? As you can see, frequency increases 1,000 times, about 1,000 times. So the power is just increased by 30 times because we can reduce this supply voltage. But if we increase this clock frequency, then we can increase also the performance of a processor, because execution time is the IC multiplied by CPI multiplied by clock period. Okay, and then so actually the clock period is the 1 over f, the clock frequency. So if we increase the clock frequency, then execution time will be also reduced, so proportionally reduced. Then that means we can increase the performance. So performance is proportional to the clock frequency of the CPU, usually, not always. So the frequency is increased by 1,000 times. That means the performance is increased 1,000 times, but the power is just increased by 30 times. Why? Because of this one, supply voltage. Okay. So how can we register this supply voltage? Because of advanced in Cmos transistor technology. That means the semiconductor technology. Okay. So, so let's focus on the here. So actually, this equation can be rewritten like this. This is the power consumption of the process, actually. Dynamic power. So dynamic power means that if the CPU is working, then the power consumption during the power, that means the power consumption while CPU is working. Okay, that means the dynamic power. So this is the same equation. The alpha means actually the activity factor. So it's the switching factor. So, and then in the previous equation, this switching factor is not shown, but if we normally use this switching factor, but this switching factor is determined by application. So actually it's usually the same. And then C means the capacitance of a circuit. So that is the area of the circuit. And then VDD means the supply voltage. And then F means the frequency. So actually the CMOS transistor is a kind of some detailed semiconductor technology. Actually, the CMOS transistor is composed of different type of semiconductor like N, P, N, and then this is the poly, so called the poly, and then based on this voltage, so this is called the gate, and then based on this gate voltage, this is drain source. Drain and source can be connected or disconnected each other. So that means this CMOS transistor is the voltage controlled switch. So that means based on this gate voltage, so gate voltage is high, then that means on. So gate voltage is low, that means off for the NMOS transistor. So there are two different types of transistor. And so actually in the transistor, it's a somewhat detailed operation. So actually this channel is generated by this voltage level of the this gate. But when this channel is generated, then electrons need to move from this side to this side, okay? And then electron moves from some distance. So that determines what is determined. So this is distance, like from Seoul to Busan or from Seoul to Daejeon. So distance is different. So what is determined? What is different? It's the speed. Okay. So actually we frequently, so when you mention about some CMOS transistor technology, we just mentioned the channel length of the transistor. So then actually this distance is the channel length. Then we can frequently also say that, oh, recently Samsung developed the 5 nanometer CMOS technology, where the TSMC developed the 7 nanometer technology. So Intel is struggling to use the 10 nanometer technology. So in the news, so this 5 nanometer, 7 nanometer, or 10 nanometer means the distance between these drain and source. That is called the channel length. So, and then we know, so I believe students usually know, if this number is smaller, that means it's the better technology. So that means the distance between drain and source is shorter. That means distance is shorter. That means speed of the transistor can be faster, because it's like some different distance between Seoul to Busan or Seoul to Daejeon. If the distance is short, then we can go to Daejeon faster than Busan. Okay. Also, there are many benefits if we reduce this channel length. We can reduce the supply voltage. Also, we can reduce the we can increase the speed of the circuit. That means that we can increase the clock frequency. Also, another benefit of this reduced channel length is that we can reduce the size of transistors. Right. And then, so in the same area, we can include a large number of transistors if we reduce this channel length of the CMOS transistor. Okay. So, so let us assume that we can reduce this channel length as 1 over S. So this S is called the scaling factor. So actually, we are learning today is a little bit tricky for some high-level students, like like some other students, some like high-level student, like some computer science. Well, so if you are not familiar with some electric engineering or electric devices, then you may feel, oh, this is somewhat difficult. It's a tricky, but it's a very it's like some common knowledge, common sense, common knowledge of this computer system. So just try to understand. Okay. So let us assume that we can reduce this channel length of the CMOS transistor as the 1 over S. So in this case, we call S as the scaling factor. So that means that we can scale down. That means that we reduce the size of a transistor by S. Okay. So if we reduce this channel length by S, 1 over S, how about the area of one transistor? So area of one transistor becomes the 1 over S square, because this is the 1 dimension, and then area means the 2 dimensions. Okay. So that means if we reduce the channel length by 1 over S, by S, 1 over S, then we can include the S squared transistors in the same area, right? Also, so I said that this C is proportional to the area of CMOS circuit. So if we reduce the channel length by 1 over S, then C also decreases, because C is also proportional to the area of this channel. Okay, so if we reduce this channel length, then C also reduced by 1 over S, also if the channel length is reduced, then also we can reduce the supply voltage as 1 over S. Okay, and then distance is reduced, then we can increase the speed by S. So that means we can increase the frequency as the S. So let's just calculate the dynamic power consumption of the processor with the more advanced CMOS technology. So more advanced, my writing is not good. More advanced technology. So it's a scaling back by S. So that means that channel length becomes the 1 over S. Okay, so C becomes the C over S, and then supply voltage becomes the VDD S, and then F becomes the SF. Okay, so if we just use these values in this equation, then P becomes the C over S VDD over S square, and then SF. So that means the C over S C VDD square and F divided by S square, right? Understand? So what does it mean? What does that mean? For single transistor, it's a single transistor. If we reduce the channel length by scaling factor S, then dynamic power consumption will becomes the 1 over S square. Okay. Oh, the power consumption is reduced. And then what does that mean? And then with this advanced CMOS technology, then we can include more transistors in the same area. How much? S square. We previously mentioned, because the size of the transistor is also reduced. So that means the power becomes the P over S square, but in the same area, the number of transistors becomes the S square. So this power means the power consumption of a single transistor. So that means in the same area, in the same chip area, the power becomes the P over S square multiplied by S square. So that is the same. What does that mean? As CMOS technology advances, then the size of a transistor is reduced, then we can increase the performance by S, okay, by scaling factor, because we can increase the clock frequency. But in the same area, we can also include the more transistor. So in the same area, the power consumption is the same. Okay, and then performance is increased by S. It's the good thing. Okay. I said the power consumption is the cost of running computer processor, but this density of the power consumption is the same. But with this same power consumption density, we can increase the performance of processor by S. So cost is the same, but performance is increased by advances in Cmos transistor technology. Okay, understand? So this is called the Dennard scaling. So Dennard scaling means that if we reduce this channel length of the Cmos transistor, then we can increase the performance by S, but the power consumption, power density of the power consumption in the same area is maintained. Okay, because the P is, for the single transistor, P is reduced to P over S square, but in the same area, we can include S square transistor. So in the same area, the power density is maintained. Power density is maintained. That is the Dennard scaling. Okay. So that means if we reduce the channel length of the Cmos transistor, then we can increase the performance of a processor without any additional cost. So additional cost means the additional power consumption. It's a very good thing. But recently, Dennard scaling is not maintained. Okay, so that is the bad thing of the Cmos transistor. So actually until 2000, Dennard scaling is maintained, so we can increase the performance of a processor without any additional power consumption. But recently, the Dennard scaling is not maintained, so that means if we include more transistors, then our chip, that means the CPU, will consume much more power. So we need to develop new idea to increase the performance of a CPU without increasing the running cost of CPU. That means the power consumption. Okay. How? Multiprocessor. What does multiprocessor means? What does multiprocessor mean? So actually, when we just mention the performance of a CPU, so actually what we learned, so in order to measure the performance of a CPU, we just measure the CPU time. That is the execution time in a CPU. So we just focus on the performance of a single CPU. Actually, when the Dennard scaling is maintained, then we can increase the performance of a single CPU as we use the advanced Cmos technology. So the power consumption is the same because the power density is the same, but performance is increased when the Dennard scaling is maintained. But recently, Dennard scaling is not maintained because of leakage current. So the problem is that if we reduce this channel length, actually when this gate becomes off, is turned off, then this channel should be also turned off. This is the off state of the Cmos transistor. But because this distance is so narrow, even though this transistor is turned off, current flows from VDD to ground. So it's like this. This is the river. So we just make a dam, the river, but some water leaks through this dam because this dam becomes weak. Okay. As this channel length is reduced, this circuit cannot be entirely off. So the current flows from VDD to ground. And then if current flows, then this current will consume also electric power. And then this consumed power is called the leakage power. Okay. So this leakage power is a serious problem of the current CMOS technology, because even though the CMOS transistor is turned off, the leakage current flows, and then the power is also consumed. So that means even though we turn off our computer, the computer continuously consumes electric power. Okay, that's the, but not always, because if we turn off some power switch of the computer system, then the entire supply power is just disconnected. But it's just some analogy. Okay, so because of this leakage power, the Dennard scaling is not maintained. So that means that if we use some larger chip, or that means some more advanced CPU, this CPU will consume more power. Okay, and then that's the problem. So how can you increase the performance? The easiest way to increase the performance is to use the fast clock frequency. Okay, but in order to use this fast clock, then actually with the same CMOS technology, in order to use the fast clock, then we need to increase the supply voltage. Okay, so it is known that if we double the clock frequency of the CPU, then the dynamic power consumed by this CPU becomes the F cube. Okay, and then this is very huge. So it's not easy to increase the performance of the CPU by increasing clock frequency, because the cost is also very high. And how can we increase the performance? Another way to increase the performance of a CPU is to increase the number of CPUs. So this is called the multiprocessors. So we frequently use the terminology quad core, dual core, or octa-core, like that. So that means that in the same chip, in the single chip, there are multiple cores. Okay, so this core means the independent processor that can execute the instructions. Okay, so quad core means that there are 4 cores. It is equivalent to the 4 CPUs in the chip, the CPU chip. So another way to increase the performance of a CPU or processor or computer system is to increase the number of CPUs or number of cores. Okay, so recently we increased the performance of a CPU by increasing number of cores. So that is called the multiprocessor era. So this graph shows the performance is the y-axis, and then this x-axis is the time, year. And then this graph shows the performance of uniprocessor. That means the single core processor. And then also you need to focus that this performance y-axis is the log scale. So 1, 10, 100,000. And then the graph looks like linear by x-axis. So what does that mean? It means the performance of a single core or a single CPU increases exponentially. And then it's very dramatical actually. But as we see the trend, so from 1980 to early 2000, the performance is increased by 52% per year. But after that, the performance is increased by 22% per year. So that means the performance increase by single core processor is slowing down. Okay. So from 1980 to early 2000, you can easily increase the performance of a single core or single CPUs. But after that, it's not easy because of power consumption. Also, the complex architecture of the single core CPU. So, how can you increase the performance? We know that if there are two people, then these two people we expect two people will do more jobs or more tasks than a single people. That's our expectation. And then it's the same to the computers. Okay, if a CPU, so it's a CPU chip has a single core, and then if a CPU chip has dual core, that means that there are two CPUs in a single chip. And then we expect, oh, this CPU will do double amount of jobs compared to this single core CPU. That's our expectation, but it's not true, right? So even though we increase the number of people or number of workers by double, but we know that the number of amount of jobs done by these two people is not doubled, right? If you take the group project, then the performance of this multiple people in the single group is not proportional to the number of people, right? Number of members. Then it's the same to the actually CPUs. Why? So let's assume that there are 4 people in a single group, but performance of this group does not 4 times of the single student. Why? Because of overhead. Also, because of some type of jobs. Okay, what is the overhead? Overhead is the communication overhead. It's a communication overhead is the first overhead, the first vector overhead, first vector overhead. Okay, and then it's the same to the CPU. Even though there are 2 CPUs in the dual core, but the performance does not double. So because of many vectors or many overhead, like communication overhead or some data movement overhead. Also, another factor is the fit characteristics of jobs. some tasks can be easily divided into two parts. That is the parallelizable task. But some tasks cannot be divided. So actually, even though two people works for this task, but we cannot reduce the time for executing this task because this task is not divided. So, and then it's the same to the computer, okay? If the application can be easily parallelizable, then if we increase the number of cores for this application, then we can easily increase the performance of a computer system. But if this task is not parallelized, then we cannot increase the performance of this task. Okay. But due to the power consumption issue, so we need to increase the number of cores in the single CPU chip, because, and then we know that recently most of our application runs the multi-threading jobs. Okay, so if we apply the multiple cores in our computer system, then we can increase the performance. Okay. Okay. Okay, I will explain until the spec benchmark. So then how then how can you compare the performance of two different computer systems? First, we need to use the same program. That means the same application. So for example, this is the computer system A and computer system B. And then for the computer system A, we launch the Windows, and then computer system B, we launch the Linux. So different application, different type of applications. And then just compare the performance. Is that fair? It's not fair. So in order to compare the performance of two different computer systems, we need to use the same application. And then the second, this application represent the various type of workload or various types of applications executed by computer systems. What does that mean? Computer runs any programs. So it's a general, that is called the general purpose. So actually the computer systems can run various type of applications. So in order to measure the performance fairly, in order to compare the performance of two different computer systems fairly, then this same program need to represent the various types of applications that runs on the general computer systems. So for this purpose, we select some applications, and then these applications are used for comparing the performance of computer systems. Then this type of applications is called the benchmark. So usually frequently called the benchmark program. And then we use this benchmark program to compare the different performance of different computer systems. And then the most popular benchmark program is the Spec Benchmark program. Okay. So, and then this Spec Benchmark program is composed of many applications like this compiler, and then compression, and then some multimedia applications. And then based on these applications, we just measure the execution time of the computer system and then compare the execution time. That means compare the performance of two different computer systems. Okay. using this benchmark. Okay, so we use benchmark applications to compare the performance of two different computer systems. Okay. Okay, so I will stop here. So in the today's class, we learned about some MIPS, it's another performance metric of the computer system. And then also we learned about the power consumption. It's a little bit tricky because power consumption is tightly related to the CMOS technology, but you need to understand how the cost to run the computer system. So it's very important. And then I slightly and mentioned the multiprocessor as a multi-core, so the benchmark applications computer system. Okay. Any questions? 네, 다를 수 있습니다. 왜냐하면은 아까 말했듯이 똑같은 어플리케이션이라고 하더라도 어떻게 컴파일 되느냐에 따라서 달라질 수가 있기 때문에 어떤 컴파일러 옵티마이제이션 테크놀로지를 썼느냐에 따라 달라질 수 있기 때문에 그거는 달라질 수가 있어요. 그러니까 최종적으로 컴파일이 된 게 똑같으면은 다 똑같다고 할 수 있는데, 근데 이제 만약 그 컴파일이 다르게 됐다라고 하면은 이제 달라질 수가 있기 때문에 다를 수 있다라고 해야 될 겁니다. 됐나요? Yeah, thank you for listening. And okay, then see you in 2 weeks. 맞죠? So have a great Chuseok holiday, and then let's meet on September 27th. Okay, thank you.